Welcome to Beyond Blueprints. I'm Andrew Smith, and today we're joined by Will Madsen, who's here from Antares Industries. Hi, Will. Thanks very much for
Hi.
joining us. And you're joining us, it looks like, from much sunnier than it is here in the UK. I'm in the very dreary Midlands, but it looks like you're somewhere much warmer. Where are you based at the moment?
I'm in the, let's call it the greater Bay Area. I'm a little bit on the outskirts, but yeah, within the Bay Area, so Northern California.
Okay. Sunny, no Cal, dreamy. And Will's here today to talk a little bit about Antares Industries. Now, Will, if somebody Googles Antares at the moment, it's very mysterious, your website. So can you tell us a little bit more about what does Antares do? What is the problem that it's setting out to solve?
Absolutely. So our mission, I think that's about all that appears on our landing page, but our mission is to provide abundant energy anywhere from Earth to the asteroid belt. What that really means is we're trying to build very small nuclear reactors that are optimized to be rapidly deployable and usable, with plenty of trade-offs in there, so that they're robust, reliable, and easy to use versus, the most cutting edge technology, let's call it, or something. It's certainly a problem more about form factor and systems integration than it is about cutting edge nuclear R&D. But that is the goal and what we're going out to solve.
Incredible. And when you say, so I can get my head around kind of the size, are we talking kind of a basketball court, a tennis court, something that could fit in my bathtub? How big?
Let's say the size of a car, like a sedan.
Okay, wow. Okay. And you can get out of something the size of a sedan with nuclear power, you can get something that is able to produce a useful amount of power in these different orbits.
Absolutely, yeah. We can get about 300 kilowatts electric based on our current system design, which it would be certainly incredibly compelling if you're going to run like a forward operating base for the DoD or something like that. I think the best thing to consider that would be like a terrestrial system that people are used to might be big diesel generators. So if you're ever at like a work site or, someone's setting up some kind of construction on a house or whatnot where you have to take out the power, oftentimes they'll bring in one of these huge diesel generators. It kind of looks like the back of a trailer on a truck, and you're constantly filling that thing up, and it's incredibly noisy and loud. We would be similar form, hopefully a bit smaller, and putting off, 2 to 3 times as much energy as your typical system like that. And of course, you wouldn't have to refuel the thing, but every 3 to 5 years, since there's a nuclear core in there.
Okay, wow. So a real kind of game changer in terms of just refueling, really, because there is no hard shoulder to pull over and just top up the tank when you're, I guess, in low Earth orbit or beyond.
Yeah, absolutely. So, that's one of the key things is we think that we're solving for contested logistics issues. So, like, it's very difficult to fly fuel around if you're in a war zone or, you're in incredibly remote locations, whether that's, in the Arctic or Antarctic or however it is, if you're in a remote place that you don't have the infrastructure to have electricity, it probably also is difficult to be constantly flying in fuel. And we do see that as an issue and have done plenty of customer discovery on the pain point of getting power to remote locations, especially because you're then constantly trying to build up the supply chain to get more diesel or jet fuel or whatever it is in there.
Okay. Okay. And so, this idea is fascinating to me because I can clearly see the problem that it solves is you're getting power where it's difficult to get it, whether that's terrestrial or extraterrestrial. Why hasn't it been done before? Kind of why now? What's the enabler that's bringing Antares into the space?
Sure. Well, I would advocate anyone watching this to go do a little Wikipedia search and look up, the SNAP 10 reactor that was launched in the 60s. So it's not the first time that someone will have put a nuclear reactor in space and it reached criticality. Like a lot of things in the nuclear industry, there are regulatory hurdles, getting things approved, getting things qualified. So I think the biggest issue of why it hasn't been done before has a bit to do with it's an interesting engineering problem and figuring it out, but a lot to do with regulatory and economic hurdles. And we think that we've reached, a point where there's a confluence of things in our favor in terms of manufacturing processes, focus on, eventually building up this high assay, low enriched uranium supply chain in the U.S. With these TRISO particles, various entrants coming in to solve some of the fuel challenges. That's normally, an incredible hurdle within the nuclear industry, as well as, so many people in the space industry are doing so many interesting things with turbo machinery, and small
Very true.
cycles for jet engines and rocket engines. And coincidentally, if you're going to be running a closed Brayton cycle or something like that in space, the the expense for small components and much smaller turbines than traditional nuclear power plants that have massive turbines that are incredible cost. Those things have come down as well, and we think that we can reach economic viability and piggyback off of a lot of the more recent work that's been done on qualifying higher temperature reactors. Higher temperature reactor running, you can make it a bit smaller, but we're not looking to have to go through massive fuel qualifications because other folks have done that over the past 20, 30 years now, as we look to build up this newer supply chain around HALEU in the US.
Very interesting. So it's not necessarily a technology itself challenge that's obviously come along, but it's the other kind of contributing engineering factors. The environment that you're operating in is more favorable, more launch platforms, I'm guessing, as well, more launch platform options. Is that factoring into kind of why now is a great time?
Yeah, absolutely. And I mean, I don't want to index too far simply on the space-based applications, because while that is incredibly interesting and something we're definitely looking at, and we're certainly optimizing for form factors that fit on C-17 aircraft, and will be able to be, pretty much deployed anywhere you can put a runway, even an unimproved runway.
Okay, amazing. So that's the why. That's the big the problem that Antares is solving. Where do you fit into the picture, Will? What is your role? What you bring to the table?
Absolutely. I'm the head of engineering. And kind of came into this position because I have a whole lot of experience across a whole bunch of different disciplines. I haven't spent too much time in any one place, so I'm more of a systems engineering type than someone who's deep diving on a specific problem. We have those kind of engineers too. We've got nuclear engineers on the team, experts in heat transfer, and what I'm doing is, being a generalist, plugging in wherever I can on helping with the design and the analysis and what are we coming up with, but focusing a ton of time on running the requirements process, the systems engineering. How are we validating, verifying everything? What are we planning in terms of test? Is that enough planning for test? Have we actually called out our risks? Have we double checked and made sure that we have retirement plans around all of these, so that we feel comfortable when we're getting into the tough engineering or economic decisions over what to build ourselves, what to buy ourselves, how many quality assessments are the right amount, and those sorts of things.
You mentioned requirements there. It's an interesting one because I imagine my knowledge of the nuclear industry is very surface level, but I imagine in terms of kind of design life and requirements, you've got quite a long horizon to account for compared to some other engineering fields, I'm guessing.
Oh, absolutely. Yeah. Especially when you're just, considering, what is your path to getting your full reactor qualified, what needs to happen there. And then how many additional requirements are you leveraging at the behest of your regulator versus just your end user? You can visualize your end user, like, let's say somebody's got a mining operation in the Arctic. They need a lot of power. That person probably cares about having an energy source that works, and that's relatively safe. So like we have to care certainly about our nuclear safety things, but as long as it works and we give them the right exclusion zone, like they're going to be happy. But our regulator has many more concerns about the inner workings and all of the materials and margins of safety and factors of safety. And we don't need to get into philosophical arguments about over regulating or under regulating or whatever is the proper amount. But definitely, as we're conceiving of the system, we want to be very aware of what our regulator is going to want to see, what kind of bit data are they going to want to see, and ensuring that even in our prototype unit that we're instrumenting and putting places for sensors at appropriate spots so that we can collect the right data, provide the right data to the regulators to make that process a little swift and easier, rather than something that's going to be very difficult because unaware of what the regulator is going to want to see, don't carve out space or methods for measuring various points in the reactor, and then coming up with, oh, I don't know, we're going to have to do a redesign to get this thing actually approved for use.
Okay, so it's quite a complex, I guess, requirements environment for from both in the life cycle of the product, but also commissioning and decommissioning. You've got to kind of be thinking about all of that before you even get into the design of the product itself.
Absolutely, 100% sure. So the concept of operations is huge. That's kind of a military term that we come back to quite a bit. But you have to know how you're going to install it. You have to know, what are the safety concerns with turning the thing on, and then how are you going to get rid of this? What are going to be the regulatory concerns about removing a reactor that you had buried in soil? What did you what did you activate? How do you get rid of that? How are you containing that? And does all of that make sense when you factor in the economic analysis of you building and deploying this thing?
I really relate to the concept of operations. We struggle with that a bit as also in aerospace because people really run their jet engines hard in certain environments sometimes, and anybody who's had any product at home, very rarely do you read the limitation instructions on the product, but I guess you've got to try and anticipate what everybody's behaving. Really interesting to hear about the technology. Coming back to kind of Antares as a team, am I right in thinking you're pretty kind of early stage? Kind of how big is the team at the moment? Is it can everybody kind of fit in a room? How are you geographically distributed?
Yeah, I don't know how much is technically inside baseball, but we are all located in California, and the team is somewhere between 5 to 10, let's say. So we can definitely all fit in a room unless it's a closet.
Okay, so you're kind of at that sweet spot of being really agile, I guess, because you're still very much there's a manageable number of connections there. And how was it? At what point were you kind of into the team? Have you been in since day one? Have you seen the team starting to grow?
Yes. So, I mean, Jordan's the founder. So he was the one person that was there from day one. And he handled, getting the company set up and the pre-seed raise. But then I was the first employee to join. So I have seen it, seen the team double when I joined. And then since then, we've been growing fast as well, but I guess slightly smaller by percentage, just by the fact that we keep gaining people, which has been great.
Okay, amazing. So are you at the point because I think often when we're talking, especially to other kind of startup companies, that 3 to 4 kind of engineer point tends to be the sweet spot, and it's the expanding. How do you maintain that good understanding of the requirements? Because if you've got a massive requirements list, you've had previous experiences in bigger companies. Is that right? So you've kind of seen it from both sides, I guess, the startup and the beyond startup phases. Interested to hear your reflections.
Yeah, absolutely. So I do have experience as a developmental engineer for the Air Force, where I was doing flight tests on radar systems, so the AWACS, which is a big radar in the sky, as well as launch operations for the Delta IV rocket, which is a big three-stick rocket made by ULA, which does a lot of spy satellite stuff because it has a super massive payload capacity. Uh, and then, since going on from being a developmental engineer in the Air Force, I worked for 4 years helping build superconducting quantum computers with Rigetti Computing. That team was quite a bit bigger by the time I joined. We had already gotten through the Series B raise, and we were at around 100 people or something like that. And then Antares is much smaller, but getting through the crux of the question, which is how do you manage requirements and alignment between teams of varying sizes where you either have plenty of touch points and sub teams, or you're just individuals working on things within the Air Force. The requirements management process has like entire organizations, uh, designed, funded, and operating on that to make sure these things flow out. And I would say that process is expensive and is not something you'd necessarily want to replicate at a private company, let alone a startup. It all kind of
Bit of a luxury to be able to do that.
Yeah, absolutely. So like they were certainly spending more in terms of risk reduction, especially on uh, the space launch events. They were willing to pay the premium to do additional risk reduction and make sure there was additional verifications, validations against all requirements, and have requirements engineers that are looking at vendors and test data and poring over these things. Uh, at Rigetti Computing, the requirements problem and alignment was quite difficult, only insofar as it was such an emerging technology, and coming up with like what is the end user and what's the valuable next thing to build, and therefore what are the requirements that flow down, was very murky. I don't know how many folks listening are super familiar with the quantum computing industry, but if you could build a big million qubit quantum computer, which is out of reach by today's current manufacturing technologies, the thing would be very useful, and you could point to those requirements. Picking something that's more intermediate is difficult, because you can do a bottoms up of like, what can we build now, but you want to always be pushing the envelope in a meaningful way forward, so that we can get to these final big systems. So the art and science of requirements definition there was, why is this a requirement, since it's not quite a fault tolerant quantum computer? So therefore you're picking something that's a bit lesser. You have to justify why that is a worthwhile target, ensure the entire team's aligned, and make sure that you're actually interpreting how a requirement for one of the subsystems actually flows up to the performance that a user is going to see, which is very difficult just because of the levels of abstraction that happen from a physical system to distilling quantum logic. At Antares, the difficulty, I would say, is just making sure that, like, while everyone's running at 100 miles an hour, that we are checking back enough and looking back at the same documents and really detailing out what are all the assumptions that we're making as we're going forward, and as we're starting to proliferate analyses and spreadsheets, simulations, doing our first CAD modeling, our neutronic simulations, like all of these things, just like anything else you'd be engineering. Take plenty of inputs that are, given assumptions, and maybe it's based on a material you're using, or maybe it's based on some pressure level that you're selecting for a working fluid, and then you're going back to your table of the thermodynamic properties, and like, if people don't have exact assumptions around like, well, what do we think our starting spec is, and how does that come from the requirement? If you're not listing these things and ensuring that everyone is aligned, when you have a very small team, everyone has so much work to do, and it's usually, it's a pretty attractive opportunity to ambitious folks that like to do a lot of heads down work. Like, that's why people generally come to startups and want to work in that environment. So ensuring that everyone slows down enough to come together and make sure that you've got, multiple tag ups a week, and that you have centralized documentation over like any assumption that you're making and starting to proliferate, that's kind of hard coded in one of your analysis, whether it's Sheets or MATLAB code or whatever it is, and just making sure everyone agrees with it, and it's a reasonable assumption by everyone's estimation rather than just your estimation. There's the whole joke about what engineers or physicists think a reasonable assumption is, and disagreements. But the main thing is, whenever you come to an understanding on something, you should be parroting that out and making sure that no one disagrees, and that your entire team is aligned on everything that is a shared assumption, and that you're constantly questioning those things so that the team is not holding false beliefs.
Yeah, no, it's very true. And what you were saying about, people join startups, they want to be part of that pacey environment where they're getting to get the engineering work done. So I guess it's quite important, especially when you're at that, early crux decision point, to have quite a lean process so people can get on with the work, and you've got enough oversight that you're managing your requirements kind of efficiently. But we all love doing the engineering, the actual
Absolutely.
technical work. So a slightly provoking question, I guess, kind of coming at that a different direction, and this could be on the kind of the technological approach, or more about how you work as a team. And let's say we had Antares and it was set up in 1985 versus Antares as it is in 2023. would you be doing it the same way, or what has changed in that time, in how you're kind of approaching the problem of power where it needs to be anywhere in the world? Big
Uh,
question, I know.
yeah, provoking question. So your solution, I think, is the same today as 1985 if you just consider at a high level what is a known technology with a very high power density that you could scale down and operate. I think that still is a fission reactor. I can't think of a better system by power density that you can operate that we understand very well. I mean, maybe you want to get kickstarted on some of this fusion work or something like that. But a fission reactor is something you can point to in 1985 and say, "I'm starting a company. I want to build the thing, and I'm going to scale it down." Now, uh, perhaps we'd be bigger. I mean, you'd have to look at what fuels have been qualified, what's going on, how is the regulatory environment around it. A lot of nuclear always comes back to that. I don't think that we are solving things with too much brand new cutting edge technology, which I think is something in favor. But I mean, you can point to nuclear submarines. The reactor rooms or whatever on those highly classified, but they're no bigger than the one fourth of a submarine, say, or something like that. So that would be what you'd point to and say what would be the best the best power source. So yeah, I suppose I'm not sure if I totally answered it correctly, but I think we'd be building the same thing. The way we're building it has definitely changed, and that's definitely the engineering tools. Why are we able to go faster than we would before? The proliferation of information just through the fact that we all have computers and are all connected, and we don't have to hand build every single software tool that we're going to use. So there's tons of open source tooling out there, which allows us to quickly iterate and evaluate different design decisions and vary things. And you just can't go that fast in 1985 when you're dealing with mainframes or whatever people were working on back then. Apologies if I butchered that one and we were already, at least on desktops by then.
I guess that ability to iterate, and I guess simulations, I'm imagining that's a huge part of what you do. How that interfaces with when do you prototype, when do you get on with the hardware versus the growing power of simulation, and how you balance those two? When is the right point to get early hardware done? When is it best to really nail your model?
Absolutely. And I think really understanding how your simulations are built. So even if we're going to be taking open source tools or whatever's in there, I want to know what assumptions they made as well, and where is something, they're just using something that's an association versus a first principles, how something is happening. Not a good thing to always point to is if you look at any simulation tool for a gas generator or something like that, generally speaking, they just assume a straight up heat transfer is happening, rather than the chemistry of a combustion event or something like that. And I'm sure that comes up in the aerospace industry a lot, just because that's
Yeah,
notoriously
absolutely.
hard to simulate perfectly. And then you say well, I'm going to need empirical data on how my combustion event happens or whatever it is. Not that we're going to have combustion events. This is just trying to pick at
Yeah,
folks
you
to be
hope
familiar.
not.
But you have to figure out what's unique about your system that is just not modeled 100% based on first principles. And if it's hard to model that thing because nature can be hard to simulate, then you have to make sure that you're making a representative test and that you're eventually able to feed in that data when you're making your digital twin. And your simulations keep getting better as you add proprietary layers on there based on data that you're taking, and making sure that you're testing, the right things that the least about, so that I always like to say that you're trimming off your margin of uncertainty. How many things are we just completely uncertain how they work, and then maybe you're over engineering something because you can't get super close to the limits on something that you don't understand super well. You want to just make sure that you're constantly cutting down on that uncertainty, and that's where you're going to be spending, your test budget versus just trying to simulate.
Yeah. Finding the kind of the holes in your verification and validation where you can kind of plug in the new data. I'm guessing. Yeah, it's something we really struggle with in aerospace as well. Actually, when to when to start testing component level and when to start looking at kind of what the integrated system does, because hardware is expensive. And so yeah, the idea of like digital twins and stuff, I think we're just going to see more and more of. um so I mean, you've got a great team, you've got a great idea, you've got the technology. What keeps the company up at night? What's kind of your big challenge at the moment? What's kind of, when Antares is lying down in the evening, what's your um yeah, what's your problem that's right in front of you?
Sure. Well, because of all of the things that you listed, that this thing can be engineered, the technology exists. We're certainly not the only very good team out there looking at this issue. I think what keeps us up is that we have to be focused on execution and making, optimized decisions on the best information that we have at a pretty quick cadence to make sure that we're building the best product on the most favorable timescale as it's going to be seen by our end customer. We think the DoD is going to be our first customer there, but they have other micro reactor projects up and running. The U.S. Department of Defense, out of the Strategic Capabilities Office, is running this Project Pele demonstration, which is focused on micro reactors. Now, those are a lot bigger than our reactor, with a smaller, more modular design versus a huge 1 megawatt plus unit. But point being is, I think what keeps us up is the fact that there is some competition.
You're in a race.
This market, and we need to make sure that we do things the best. We're the best stewards of the capital that we have, and that we are, executing quickly, but with the appropriate amount of engineering rigor. So of course that we're not, falling on our face by trying to go too fast.
Yeah. So you've got the dual pressures in a way. You've got the end customer who obviously wants to see something, and then you've also got other people kind of rushing towards that customer. So you're feeling the pace from a kind of pincer movement.
Yeah, I think that would be a way to describe it. I mean, like, we've gone through iterations on designs and what's possible, and we always try to come back to what can we leverage that's already been qualified by regulators in the nuclear space. So whether that's the DOE, that's the U.S. Department of Energy, or the NRC, the Nuclear Regulation Committee in the U.S., and like trying to make sure we're using as many components and items within the limits of things that already exist, so that we can go, faster to our first prototype unit. And then we can, after we have a system that works, we can work on, how can we push the boundaries and limits, and how can we engage to get new things qualified, and like really, blow the doors off what this technology's at. And but the point being is, to get to that, we need to make sure that we are turning over every stone, and that we're not putting anything too exotic into our first system.
And I mean, you mentioned kind of first customer is likely to be kind of DoD. That's like going in at the deep end, right? That's not a kind of nice operating environment. So I guess that's a really demanding requirement set to have as a kind of entry into the market.
It is interesting. So my background is in the DoD. Certainly, I'm used to playing in that swimming pool. They are a demanding customer. I think there's been a lot of focus in the last 10 years on non-traditional contractors, so startups and others engaging with the DoD, and the DoD trying to make systems to engage with small businesses and various offices that call themselves the front door to X, like the front door to space, or the front door to Air Force Research Lab, or whatever it is. So they certainly are working on improving processes to engage with smaller companies. And I think there's a lot to like about the DoD, both in the facts, both in the way that they are a demanding customer, but also in the way that, they have pioneered a lot of technologies. If you look at the history of DARPA, the various research labs, but like the DoD likes to take bets on emerging technology. Some of those they solely use themselves. Some of those make them to dual use markets. Certainly, we'd like to be in that category. But they're a customer that has demanding requirements, but perhaps they're not as price sensitive on the first of a kind unit uh, as some kind of commercial customer might be. So so I don't know. It is it is tough. It's not always the easiest to sell into the DoD. There's definitely big companies that are competing with us for those exact same contracting dollars. But I think there is a lot to like about the market opportunity.
Yeah. Interesting as well that as a customer, they also, I guess, have been it maybe it's a different division, but they've been a developer as well. So they're used to making and designing to requirements. So I'm wondering if that also makes them kind of quite tricky because they know what they're talking about. They know what are the requirements. It's not kind of vague customer. They've got quite a laser focus on what they want to do, which could be good and bad. I guess it gives you a clear requirement set, but it means it's quite uncompromising.
Absolutely. So I think the way to envision it is like, look, if you're going to try to build a new system to the DoD, it's not just a commercial offering or something that just is off the shelf today. Like you're going to be building something with the DoD. They have a fleet of engineers and world class scientists, and they put the resources behind it to ensure that this is like a core capability, and that whatever they are buying and bringing to market, that it's exactly what their user is going to need, and their user is somebody that's in life or death scenarios. So they are unrelenting on the requirements, and I think for us, uh, that's great. I mean, I want to build safe nuclear systems that can be deployed all over the world, and certainly, if we can build something to the DoD standards, I think that we're going to be in prime position going out and eventually trying to augment that design to make it more palatable to the commercial market. So I'm excited to partner with the DoD. Like they have all of this expertise already in house and all of these engineers, and like I consider it an honor to get to work with them. And hopefully we will pick up the right contracts. So just that will happen.
Yeah, yeah. It's so interesting. With the DoD, the requirements are clearly so important. So how do you maintain? You said you got to keep this laser focus on kind of delivery and route to products. How do you keep that kind of end goal in mind? How do you maintain the kind of visibility of ultimately what the product needs to do? Is that through these kind of regular reviews? Is that through kind of people really regularly talking about the requirements at kind of the system subsystem level?
Yeah. So I mean, I like to structure things as much as possible as an engineering project where you're working towards various milestones, and then you're having reviews that are milestone driven rather than like arbitrary points on the schedule. So you want to get a certain amount of things done and different work streams done and have simulations done or whatever it is, and then you want to review that work and always come back. I make sure that requirements are a focal point of any and all reviews. So like just up front when you're discussing what will we be reviewing, what's the point of this, why are we all getting together, and even though we're a 5-person team and we talk every day and we're constantly together, like why are we having a more formalized meeting thing where we're going through a deck and going over the results and somebody's presenting all the work they did. We want to point to the requirements. We needed to validate this thing about the core, or I needed to confirm that this was the assumption that we had made in the working fluid for our power conversion unit. And, sure enough, everything looks favorable, and just making sure that you're always pointing that back to, this was the unit of work that was being done, or, maybe this was around test planning. And, these are the sets of tests that we are going to be reviewing today, and you can link those directly to these requirements, which end up if you follow the chain to like the parents, that like this is what the user is going to see and this is why we're doing this. So I like to make sure that you have milestones, you're reviewing after milestones in some kind of more formalized way, even with your small team. Like I think it's important to put that kind of muscle in place, and that anytime you're holding a review, you're pointing back to the big picture of why this matters, and that usually comes down to the requirements.
Yeah, yeah, they're at the core of everything. So, with all that in mind, I mean, you're And I forgot to ask actually, kind of, and I don't know if you can talk about kind of timelines or what you're shooting for. If you can say decade, I don't know even what you're shooting for, or if that's all under wraps at the moment.
Less than a decade, certainly. I don't.
Okay. Oh wow. Okay.
Yeah, we're certainly targeting less than a decade. I don't know, given our current stage, how much more I can divulge, but well
That's
less than
that's
well
okay.
less than a decade.
But fast for nuclear. That's amazing. How do you see, as we're kind of coming to the end, it's been so interesting to hear about this. Well, how do you see the future of engineering? And broad question, but specifically, I guess in the industry that Antares is playing in, where do you see things going? What are you excited for?
I am excited, for the entire push for. I guess it's a slight renaissance for small modular reactors, micro reactors. Uh, that word wasn't even in the common parlance, I'd say, about 5, 6 years ago. So it's a relatively new concept that it's actually economically feasible to build reactors that are not power plant scale and that are well less than 10 megawatts. Uh, and seeing that pushed forward, I think gives us so much opportunity to uh, kind of really thrust into a second nuclear age. I mean, that's probably a bit of a buzzword, and you might hear that get thrown around by other folks within the industry. But the promise of nuclear back in the day was that we'd have all of these boundless energy sources, and consumption would be so high that it wouldn't even be, a concern. Obviously, one of the biggest concerns facing all of us in the world is power consumption. How are we generating power, and what is that doing to the environment and world we live around? I think more nuclear will solve a lot of those, and I think that doing that in a safe and reliable way, will be not non-trivial for the way we live. I mean, first you solve this problem for remote circumstances. I think eventually, energy eventually comes down to microgrid scenarios, more distributed power generation, and I think on the grandest terms, it just allows people to live better. Like if energy and the cost of energy is no longer a concern for people, imagine how many more things you could be doing. It could be quite amazing. So I think not only that it solves current scarcity issues and climate types of problems, which is definitely a big part of our mission. It's the fact that abundant energy for any person, no matter where they are, would be profound in the way of life and how they can live.
It's got a key role to play in the energy transition. And that question from a slightly different point of view, then. So that's the technology feature in terms of, if you were to fast forward 10 years time, how can you see how we as engineers are going to be working differently? Or what would you like to see? Maybe that's a better question. What would you, the thorn in your side that would just be amazing if it could just go away? And it doesn't need to be about requirements. It could just be about the world of engineering today.
Yeah, absolutely. I think the biggest thing is more collaboration, more collaborative tools. The fact that all engineers can be sharing models and simulations. They're easy to work with. There's more open source tools. Uh, Even just being able to pull things up on your computer in terms of going back to thermodynamics tables or anything rather than having to sort through a book.
Thumb through the old textbook. I think I've got one of them over here, a kind of thermodynamics reference book. Just out of shot.
Yeah, it just lets you go so much faster. And then the fact that the just proliferation of preprint servers and allowing people to easily read into the science that's being done at the cutting edge all across universities across the world. I just don't think there was that much access to that type of information, even 15 years out, unless you had niche subscriptions to many different journals and periodicals. And those types of papers are prevalent in everyone's engineering job these days. And, reading through, seeing what this group's doing, that group's doing. So I just think that speeds us all up overall, uh, and allows us to, iterate faster because you don't have to solve every single fundamental science issue, and you don't have to write all of your own software to start investigating things. You can start tinkering, as fast as possible, and then you can share those results out, and people can, iterate in real time with you rather than having, to download and get a courier to hand over some papers or a disk to someone for them to upload into their computer and start working. So I think like there's always plenty of like a chorus of people out there that like with the space industry and the resurgence of that, or the nuclear industry, that like, oh, the course of development has kind of gone awry since the 50s and 60s when we were doing all these amazing things. Uh, I think we may have focused on the right problem first in terms of highly developing all of the networking and internet technologies and compute power. And we've gotten to a point where it's very easy to have almost any information at your fingertips. So much so that like it's a real skill to have a good filter on whether the information is valid or not, and being able to share those things, and work in real time seamlessly as possible. So yeah, that's where I
It,
think
it,
the
it
future
I
engineering is going.
100% agreed on the collaboration. The something I struggle with, and it just sprang to me then when you were talking about access to research. It is incredible. Something I sometimes struggle with is just the volume. So it's like you've opened the taps. Is knowing how to keep abridged of all the developments. I certainly feel like that in aerospace, is that there's so many studies to kind of triage that it's a blessing, but it can feel like a curse sometimes as well. What to pay attention to in terms of developments in the space. I don't know if that's the same for you, and kind of the latest reactor geometries or materials, all that kind of stuff that I guess you've got to keep an ear out for, but you've got to balance your time.
Yeah, absolutely. I think almost every single field is inundated, and that's just because everything is posted preprint now, which is net good for civilization, net bad for engineer that needs to filter through 20 different papers and pick which one to read, since they're all 7 pages long with additional figures and appendices.
Yeah, that's a universal problem all engineers can attest to. Um, Brilliant. And before we leave, I've got to ask, and I don't know if you can say this, when will we be able to read more about Antares, or is that very much all under wraps at the moment?
um, you should be able to see and read more within this year.
Okay. Very exciting. Very exciting. Got to keep the cards close to your chest. Thanks so much for joining us, Will, on Beyond Blueprints today.
Thanks, it was great.